So howdy and welcome back. We're going to continue our discussion by more or less reviewing the allocation of memory to variables on the stack. So you might remember this diagram here. We'll run back through it quickly, but recall when a function, for example, main, calls another function, such as maybe that factorial function we wrote or built up during the previous lesson. An activation record, also known as a stack frame for the called function, gets pushed to the stack. Now recall that this allocation is performed by the stack pointer being moved in one direction to allocate stack memory for the parameters and local variables associated with an instance of the function that was called. Keep in mind there's some additional housekeeping information that's also stored within a stack frame or activation record, as it's also known. But we're kind of ignoring that here. But you'll probably get into that in a later course. Furthermore, recall that when the function finishes executing, the stack pointer is moved back in the opposite direction. In this case, memory is deallocated. So you can think of the stack as a growing and shrinking array of heterogeneous objects, that is, function activation records. So recall that when main boots up, an activation record is created for it, and the stack pointer points to it. When we move into, say, our factorial of 3, memory for, in this case, the single parameter end, gets allocated by the stack pointer moving up. In this case, let's assume 4 bytes. Because let's say that's the amount of space required to store an integer object. Notice here that we make a recursive call. So another instance of fact is invoked, and the memory for that particular instance is stored in its own activation record. So notice here that the state of fact3 is preserved because its activation record is still on the stack. We've only added a record on top of it. And we'll do this one more time as we make that recursive call here for fact of n-1 or fact of 1. So in this case, the stack pointer gets moved up. And recall that now with a n value of 1, we've reached our base case and we begin unwinding. So we return -1 to fact of 2, and memory is deallocated for fact of 1 as the stack pointer is moved back in the opposite direction. So at this point, we pick up where we left off in fact of 2. That was right here where we made that call to fact of 1. And now this function call, we've returned a value so we can kind of fill in the blank. So we have, in this case, 2 multiplied by 1, and that gets returned. Well, how is that returned? Well, the value gets returned back to the caller, and the stack pointer deallocates the memory associated with fact of 2's activation record. And it looks like I made a mistake here. This should be fact of 3. Sorry about that. Okay, so now we're in fact of 3. We're going to pick up where we left off, which is on this statement here. Notice we preserved the value of n in this case. So we have 3 multiplied by the return value of fact of 2. So 3 multiplied by 2. And that's going to be returned to main. So 6 is going to get returned to main. And when we go ahead and return, that stack pointer is moved back in the opposite direction. And in this case, result takes on the value of 6. So with that process in mind, let's go ahead and trace the execution of the following program. And I'm going to use a bit of a different diagram to hopefully illustrate some of the components and how the stack changes with a function call. So let's trace the execution of this program. It's simply a main. It's going to have 2 variables local to it, I and z. Both are going to be integer, refer to integer objects. I will be initialized with the integer value of 10. Z is going to be initialized with the value returned by this function times 2 of I, so times 2 of 10. Times 2 is a function that's simply going to go ahead and take in a single integer argument. It is going to multiply that argument by the integer value of 2, storing that value in a local variable, R1, and R1 will be returned to the caller. Okay, so let's start looking at how the stack's changing from directly before we begin its execution. So before, I guess, main's loaded into memory and we begin executing it. So at this point, the stack's empty, the free store's empty, and all that's kind of out. There's the code and static data. So we launch main, and if we're going to jump into a function, well, we need an activation record for that function. So, you could pause the video and think about what this would look like. Again, the ordering of the actual variables within, say, the activation record is kind of up to the compiler, but we'll go ahead and just put them in order of declaration, which is relatively common. So we hop into main. We can see that the activation record of main is going to span 8 bytes on the stack. And we can see that the stack in this case is growing down from the upper end of the address space allocated to our program towards 0. So this whole region right here, can't really see that. I apologize. Let's use yellow. It's a funky color, but this whole thing that is highlighted there is going to be the activation record for main. And notice that it essentially has enough data to store both I and Z. Okay, so, I is going to get initialized with 10. Z, we have a blank we need to fill in. So what is Z going to get initialized with? Well, it will be the return result of times 2 of I. That means we need to pause execution of main and move into our instruction set, or our series of instructions associated with the function times 2, and eventually get that return value and assign it to Z. So times 2 is essentially invoked, and we move into it. Notice here that the activation record for times 2 is going to be 8 bytes, 4 bytes to hold its integer parameter T1, 4 bytes to hold its local variable R1, which is also an integer type object. So in this case, we're going to see here that the activation record for times 2 is going to span 8 bytes, beginning at that pointed to by the stack pointer. So if we go ahead and look at this, that is the activation record for times 2. One thing to point out is this is kind of like, we made the analogy of it being kind of like an array. Notice here that you could theoretically, if you kind of know how to manipulate this, access main's activation record from times 2, because this memory here is contiguous. So if you get outside the bounds of the activation record for times 2, you're in the activation record for main. And this is why you could pass by reference, because the actual variables, say, associated with main are, guess what, still in memory. So you're able to bind a name local to, say, times 2 to that entity that resides in a different activation record. But notice here that's not what we're showing. That was a slight aside just to point out that, hey, this kind of block of memory is contiguous. The stack in this case is growing down. And what that means is if times 2's activation record is on top of main's, well, it's on top of main's, and that if you get outside its bounds, you're now into main. So what happens when we return from times 2? Well, in this case, the stack pointer is going to be brought back in the opposite direction. Now, if you recall from the previous lesson, I mentioned that, hey, C++ doesn't zero anything out. So technically, at this point, when we've returned to the activation record for main, R1 and T1 in these places in memory still hold their previous value. And again, the reason for that is that C++ does not zero out those bytes of memory. However, the second we invoke another function, recall that we're going to just add on top of main. So this space here, all the way up, I mean, until we essentially have a Stack Overflow, is going to be kind of reused or used for the first time. So I'll show you an example where this could become problematic if you're doing certain things, but let's hold off on that. Just keep this kind of in mind. But for all intents and purposes, you should think that once the function returns, the memory for the local variables and parameters is deallocated, even if they're kind of still hanging around until something else writes over their previous location. Just don't mess with them. Memory's been deallocated, and that it's now available for the use of something else. So just view it. You return from the function, whatever data was stored within those local parameters or local variables is gone. And that's what I'm showing in this diagram here. So the question, probably becomes at this point is, why do the size of objects stored on the stack have to know their size at compile time? And we'll answer that in the next video of this lesson.